Hello and welcome to the third lecture in our series. I had to split it up in two sections, which is why I'm making this little beginning section. The first section will be me giving the presentation as normal, and the second section will be me going over some corrections for the presentation because I felt like it was necessary for this presentation. And it'll be pretty clear between one section because the first one is me giving a lecture at a board. It's a full screen. Second one will be me giving a lecture in a PowerPoint,
Okay.
and
We're starting.
I hope you enjoy.
Reset. This week we will help to understand how a black hole looks and finish our discussion of relativity. As a recap of last week, we reviewed action as a fundamental idea in science and began to talk about this concept as it relates to black holes. Firstly, I wanted to define a geodesic. We can represent black hole geometries as a composite of many geodesics. So, geodesic, do you remember what we were talking about with the path of least action, or the path of like minimal deviation from the path of least action? So geodesic is specific to what light takes as its path of least action. It's saying assuming light always moves in a straight line at the same speed, or I guess just saying assuming light always moves at the same speed, what shape would it have to go to be that, or like what shape would the space around it have to be, or space time around it to be to make that shape that shape? So like if light wants to go like that, and then there's it's like really gravity here.
Oh my.
But this is like the surface, and this is the path light takes. But this is the surface, then light would go like, well, I don't know, it would go like, whatever. The concept of that light changes, yeah, okay. Just in case you didn't understand.
It bends.
But there's something faster thing. Okay. So this also brings back to black holes and time dilation. If an astronaut takes a path of least action, whatever, could be a saddle point as well. I think I maybe briefly talked about that last week. That saddle point is where it's like a way where it can be least action without it being like minimum action. Like the caveat to it's saying it's a path of least action, just saying that can be a path of saddle point action or whatever. But saddle point is like a geometry thing where it's where the first derivative of it is flat, but it's not a maximum or minimum. So you might know that as like I forget the name of it. There's like a thing in calculus where you do that. Like if you don't know what the derivative is,
it's called a saddle point.
yeah, okay. The derivative is the slope of a line.
Yeah.
It's like a function of the line. So derivative is, or if the function is f of x equals x squared, then the derivative or the prime of f of x is equal to, well, for this case, it'd be 2x.
Oh boy.
But you don't know how I got that probably. Basically, this is the line like it would take. So if this is the curve, then the line it takes, or like the line it's increasing at, it's like that. You can see it has a negative slope where x is negative, and then as it progresses, it goes positive. So this isn't like this should be further down, but I just want to say it's good. But like, does that make sense? So a saddle point is where it's like it's at that, but it's not where there's a minimum. So it doesn't. But like, if you have like a if you have like that or whatever, and you want to take what's the minimum of that, then you would say here. Like you would bring it out like this, and then you say here. That's the minimum. But if it was something like, oh, what's the minimum of this whole thing, then it would have something called a local minimum. Depending on where it is. So if you took it from here to here, then the local minimum would be here. Or whatever. Maybe, I guess it'd be here. So that's an endpoint. But then, like, yeah, so this is a minimum. But then if there's like, if it's two end bounds that are like that, then there's a local minimum here, even though it's not the minimum for the whole thing. So this would be also a point where it's the least action. So another thing to keep in mind is that least action is all about probabilities. You see this at like only on the scale of like atoms and stuff, but atoms don't always move according to least action principles. Space is, or like matter is laid out so that you might have heard entropy, the idea that the universe is like expanding and that thing like energy is trying to expand, become most balanced. So if you have like two positive charges next to each other, they'll move away because it takes more energy to keep them close than does to keep them apart. Or more action. Now you can see why that happens. It's like the same principle. So, but this is like a probability because it doesn't have to at the scale of atoms. Like if you have, say you have two atoms and there's an electron orbiting like, okay, whatever. This is a Harrow diagram that I forget, but imagine it's like orbiting between them. And it's like going, if you add an electron to this one, like, sorry, let's say this is hydrogen. These are both hydrogen. This one's hydrogen positive. This one's hydrogen neutral. If you add an electron to this, the path of least action would be to transfer this electron to this thing. But this is a bad thing. This doesn't actually happen for hydrogen, but for atoms with many electrons. What the hell is that? The electron can stay here, and it'll just be two. So it's, but then it'll maybe circle around and then go to the next one. Because all probabilities. But the reason that you don't see this, like electricity doesn't always go from most charge to least charge. The fusion doesn't always happen where the thing with most goes to the least thing with fewest. It's just that if you look at the probability of that happening, there's a little bit of stats. As the sample size increases, the standard deviation decreases, or the spread decreases. So it becomes less likely that like you can't see it. Like at a scale of we're at, it's that like everything happens how it should. Things don't fall out. But at the scale of atoms, sometimes that cannot happen. This is me correcting a bit of what I told you about last week about action because I think it wasn't very clear. Nothing about what I said was wrong. It was just maybe a little misleading. So I want to correct that. So anyway, back to black holes. If an action takes a path of least action through space, and the space-time plane is curved by a black hole such that the astronaut falls through it. So this is a black hole. Whatever. Bear with me. It's like, oh boy. Whatever. And it's like, whoa, I want to go away, but oh, gravity. This is an observer. Well, I guess that's kind of a bad observer because they can't see through the black hole. But this is an observer here. Well, I guess they also, this is what I'll get to, but they also can't see it. Whatever. You get the idea. This person is like, or like, this observer is like up there. I hope the camera can see it. Like, all in there. They would see the astronaut accelerate, or in their respective accelerate, or decelerate. I guess not. Sorry, they are accelerating, but it's negative accelerate, like negative acceleration, so it's decelerating technically because I guess it depends on whatever. Semantics. Semantics. Yeah. As they approach the event horizon, while the astronaut would not feel not feel acceleration at all because they're just falling. This is just the path of least action through space-time. They're just going along on their merry way. They wouldn't feel themselves accelerate relative to other things near them. The observer would see them decelerate. So like this person looks like they're slowing down, but to them, they're just moving at constant speed. If they have their eyes shut and they're not looking at the black hole they're rapidly approaching. So going back to visualization of black hole as a well, which is like, talk about it here. Whatever, I'll show you. Like this, it's like a well. See, it's like a well. Light takes longer to reach the observer the farther down the well it reflects from. So you see, like the singularity for the event horizon is like it's not just at like where it starts curving down. It's like a little bit past where it starts curving down. It's a little bit past the tip of the well. So this tells us that from there, like light takes longer to arrive to them than it like if you're trying to get light out of it, it takes longer to arrive to the observer than it does for the person, or than it would if there wasn't a black hole there. Well, this is like, if you think about this, this is kind of what time dilation is, where like the closer, like basically it changes time relative to where you're at the black hole. And this idea of time dilation doesn't end at an event horizon. Like just because you go past, just because a little Timmy goes past the event horizon, doesn't mean that, oh, time's normal now, everything's good. You know, it's not like whatever. I'll explain that later. But like time dilation gets really, really weird when you get in the black hole. It kind of reverses space and time, where space becomes your future and time becomes the thing you move along, instead of it being space is what you move along and time is like your future. Does that make sense? Which is like the idea of you're destined to go to the singularity if you enter a black hole. So once past the event horizon, you would think, you know, oh, I can escape. No, you can't escape. Sorry. That's kind of like the definition of event horizon. Actually, even if you're like not even past the event horizon, the chance of you escaping is, well, I did a calculation for specifically Interstellar, and maybe I'll get to that later. That's not really like the type of thing I was researching that much, but I did put that in as a calculation where it was finding how fast the spaceship they were taking would have to accelerate to escape the black hole if it was just going in a straight line, which it wasn't. It was going in a circle. Doing a circle for a black hole, escape velocity is ridiculously difficult. So I do not want to learn like graduate school level calculus just to do that. But basically, if you do that, then you have to approach basically the speed of light. Like you're not at the speed of light, you got to approach the speed of light to do that. So they couldn't really have done it, but that's okay. But like the idea is that you don't, like, even if you're here, you're probably still not getting away from the black hole. You're just kind of, you know, you're screwed. So you want to think about mathematically the reason this would happen, or like, yeah. If you are put in the path of the black hole, something called your light cone becomes it becomes so slanted, I guess, in space-time that the black hole becomes your future. That's what the singularity, like, that's the idea of a singularity, is that after a certain point, the singularity becomes your future, and you can't escape. So you might ask, wow, that seems weird. Why is that? Well, look at this diagram. This is a fraudulent diagram. It's correct, but it explains it in a way that doesn't really make sense intuitively. So did I talk about light cones already or no? Like, no. I need the lectures. Okay, and so a light cone is if you have one point into space and one point into time. So, well, I guess this just shows it, but this is space, this is time. Then light cone is the path in space-time that you can take from any point. So it has like circles going to show it's a cone, but it's not, if it's doing one corner of space and one corner of time, it's really just a triangle. But it does have like, I guess it has an name, so whatever. But you'll see that like distant away from the black hole, it should be a 45-degree angle because there's one corner of space, one corner of time. You're just going through space and time, I guess. And there's nothing really to warp space-time. There's no gravity, or there's no effective gravity because there's no mass. This is assuming that you're not near like a planet or something. If you're near a planet, it's different. But for our purposes, even if you're like on Earth, the amount that it changes your space-time is like so minimal. Like it changes your ability to move as a human. But if you're just like an object, any object, like gravity is such a low force that it doesn't really affect. It only affects on the scale of extremely large cosmic objects like black holes. But you'll see that like the idea is this is one point. Oh, I'll just draw this on the other diagram. It's easier. If you just have if this is space-time, I'll draw the full diagram just so you get an idea. If this is space-time, each horizontal line, that's terrible. Each horizontal line is like that. And each vertical line is like that. So this down here represents past time like infinity. Or if you go back to the beginning of time, like basically the unreachable past. you can never reach this point in time, because what if you were born here? What you're just gonna go back in time, you can't do that. So if you look at like what this creates a cone shape or a triangle shape. It's a cone. And if you're doing 2-dimensional space. And this is the possible paths you can take in space-time from that point. So the reason it's a cone is because it's like if you shine a light basically from where you are, like if I shine a light on all directions, if I start glowing like a god in all directions through all of space, then that would show you my light cone, because that is the path because light is the maximum speed, so it's the path in space-time that it can maximally reach from any given point in time. So a light cone changes depending on where you are, when you are, mostly just where you are, because when doesn't, as far as I know, change like gravity or whatever. Maybe it does if you're like weird or something, but so like it's a triangle shape because you have one point in space, one point in time. So if space is this way, this is like infinite space. This is space you can never reach. This is also space you can never reach. But we all live in here, all of us. And you might be asking, well, what are these three things? If this is our entire universe, and we are living here, whatever. This is like, yeah, whatever. You can see the coordinates. It's fine. If we live here, then our light cone can never reach parts in here after a certain point. So after we get to here, or actually never, no matter what point you are in here, you can never reach one of these. You can never reach one of these, because you can never have a light cone point that goes more than 45 degrees through one-dimensional space-time, or two-dimensional space-time, I guess. But it's like one dimension of space, one dimension of time. This is all like subjected to what we consider dimensions and stuff. But sorry, what question?
So what are those? If that's our universe, are those like separate universes?
This is a black hole. Once you pass the event horizon, I'm not gonna. I forget if I have a diagram of this in the PowerPoint. I'll check. Well, that's annoying. I don't. Whatever. Maybe I should have prepared better. That's okay. This is a very bad point for me because I'm bad at drawing these graphs because they're annoying. But just like think of like it's just like that should be a square. So, but
Rhombus.
if you have, whoa, what am I thinking? Okay, there we go. I was tweaking out for a second. This is us. This is this past time like infinity. This is future time like infinity. As you approach here, the lines become like more curved and such because you're accelerated different amount as you're trying to approach. This is like future space time like infinity. Or the event horizon. This is the event horizon. So
that's future and the bottom is past.
yeah, this is the future. It's like a maximum future, but you can reach this, but like the idea is once you pass here, you can't go back to here because then you have to change. You have to go more than 45 degrees horizontally. So the idea of light cones is that it's the maximum ability of you to escape where you are now. And if your light cone goes to a certain point in space-time, all this is terrible diagrams. That's completely confusing to you guys because I did it wrong. But like all the concepts I'm saying are correct. That if you go to a certain point in space-time, some points become your future and thus impossible to escape from. Like, yes, sorry, question.
So is it like a pawn in chess? You can only go forward or diagonally forward? You can't go backwards. That's like what a light cone is?
I mean, yeah, but I wouldn't call it a pawn chess because that implies there are ways to change, like there are ways to change how you move because if you accelerate, you don't just go always 45 degrees because I don't just stand still my whole life and I just go through space time I'm walking, I'm accelerating. And that means that I increase acceleration and therefore I change.
But like you have the range of motion of a pawn's chess.
No. I don't like that example.
I think
Could you think about?
I think it's like the papers.
Could you think of these four quadrants?
That is fun.
Yeah.
Hello. I am making this section of the presentation or the lecture to correct some of the stuff I said because I thought I did an insufficient job in explaining it on the recorded lecture that I made on the last one. The one right before I'm talking about this, so you'll see. I previously last night made another. I made a full lecture containing all the stuff that I want to talk about, and then the audio file got corrupted. So this is my second attempt doing this. I made sure the audio worked this time, but it might mean that it's a little more brief maybe because I feel like I've gone over a lot of this stuff. It's just my memory. But I figured I should start with an explanation of kind of what I got wrong. I think the first half of the video, up till about 13 minutes, I think I explained very well. I explained like the basics of light cones and explained relativity. I basically ended our general discussion about general relativity. And then I went on to I kind of jumped the gun based on a question, I think, about like how to visualize this on like a graph or whatever. But I talked about graphs, and I drew an incorrect graph, which I'll get to why it's incorrect. But I figured I should probably go over graphs. I'm going to have a whole section on graphs later when I talk about wormholes, and I talk about other cool stuff that arises from black holes. But I figured because I touched at it in the lecture, I should also explain like the basics of it and also help you to visualize it because it is important and it is cool. So first, you'll see here on the screen, we have, oh, I should get the, wait, no? Where's the laser pointer? There we go. I should get the laser pointer. This is a translation of a kruskal-szekeres diagram or a KS diagram, which I try to call it, but often I just sing the whole thing because I forget, but KS is quicker, and most people say KS anyway. It is the kind of the basic, I showed this in the lecture, I believe. It has one time coordinate, it has one space coordinate, and it's the radius from the black hole in the time. So I said it was faulty, and that is partially correct. I think I mentioned that, but it is correct in terms of mathematically it all works out, but logically it shows that space goes to infinity at a point, or it has a specific line here, which this specific version of the graph, like I just pulled it off the internet, it doesn't actually show it, but there would be like a line here, like it would be like a limit that you would see in like other forms of math, and that doesn't obviously happen in nature. So what gives? You know, it's incorrect in some ways, in some ways because it's hard to visualize it compared to other forms of graphs. The common KS diagram is one I'll show in a bit, and it relates to Schwarzschild black holes or non-spinning black holes. There is an important distinction between non-spinning and spinning black holes, which I think I'll get to. I was going to be my next lesson anyway, but I think I talk about it in this because I talk about different diagrams and such. But you can see the event horizon is basically defined as the point where light cones are tipped horizontally. It doesn't really show like what the point where it's completely horizontal, but it's like this is how it normally is, and it's like far away from the event horizon. And then as it gets closer to the event horizon, your light cone becomes more and more stratified, I guess, and then it eventually it flips the coordinates of space and time. Or I guess it's kind of the outcome of it, but like you can see how it just makes it so that it's wider and wider until it passes, and then it becomes horizontal. And that's when you get this being the future, and you would think that, oh, this is like normally the future is a place in time, but because light cone is horizontal, it means your future is a place in space. Like basically, your light cone is directed towards a space, and in time is like how you would be normally in space. Which sounds confusing. It's a little confusing, but essentially, when talking about light cones, you kind of think of it as like a summative thing, and or at least I think about it as a summative thing. So when I think about it's your future being the um, the singularity, which is what I guess I didn't mention that, but this is like the idea is that past the event horizon in a non-spinning black hole, the future is your singularity, or the future is the singularity of the black hole, which is like the center, I guess, of the black hole, um, mathematically. And I think of that as there's no path in space-time that you can take to avoid going to it at this point because of the gravity it has, or the acceleration you'd have to escape going towards it. It's kind of just like a well, like you're stuck going down the well, um, even if you're trying to get it. And then the next slide, I think I'll go over the basics of something called the Penrose diagram, which is a translation of the kruskal-szekeres diagram. Um, this is the basic Penrose diagram, um, and it depicts a spinning black hole, not just a non-spinning black hole. Although it can also apply to non-spinning black holes, it's just kind of strange. So I'll explain that. So here you can see the Penrose diagram, and I'll first go over like obviously what it's showing. So um, it shows this is the thing I was actually I guess it's not really the thing I was trying to draw. It's a section of the thing I was trying to draw. You can kind of think of this as, or I guess you should think of this as our universe, basically. Our universe, nothing else, no added things, just our universe. It has a past time like infinity, a future time like infinity, and then a positive space and negative space like infinities, which basically means there's a past infinitely in the future. There's a sorry, whoa. There's a past infinitely in the past, or a time infinitely in the past, and there's a future time infinitely in the future. And these are two places you can never reach as a normal being. There's something called an immortal being, which is used for diagrams like this, where you track basically you start here and then you track their path through space-time. Um, but I'm not going to get into that today because I just wanted to go over the graphs and not really get into the relation between them. But that is an interesting part of general relativity, so I might address it at some point. It's also part of a book I'm reading. I like the book a lot, so I might just talk about it because I like the book. It's called Black Holes by Brian Cox. I believe I mentioned it in either this lecture or the lecture I'm correcting today or the lecture from last week. Um, but anyway, so when it says negative and positive space like infinity, that just means parts of the universe that are infinitely far away from you. So you should also note that light cones move from each point, and the reason that it kind of looks like it has like the bending lines is because obviously it goes to infinity. Um, the Penrose diagram is a translation or a coordinate transfer of the kruskal-szekeres diagram, which is the one I just showed. And that kruskal-szekeres diagram is like the basis for a different space-time diagram, which I'm going to get to later, which kind of looks like this, but it doesn't have these lines here. The reason the Penrose diagram is used for non-spinning black holes is because it's easier to compare stuff when you take away, um, when you add these boundary lines. The basic KS diagram does not have these lines, and it shows it kind of maximally extended, I guess. I had to say max. I don't like to say maximally extended when it's not like the direct term for it, but I would say it's maximally extended. Um, and it kind of shows the warping of space and time relative to you. Um, so you'll notice there's like a center here, and you might think, oh, that's just like, what does that mean? Like, what does a center in space time mean? So people can use this interval between the future and past. That represents where you are presently, or like where the thing you're measuring is presently. So if I'm measuring myself, then I would say, I don't know, I start here, um, and I can track all the things I do in the future or past, or I can't. Sorry, I'll track all the things I can do in the future in space time. Um, and I can see what I did in the past. Like if I start today, I can see what I did in the past by going to this section. But for the universe, which is basically what we measure, if we're measuring black holes, we're measuring the universe. We'd measure this at just like the kind of neutral point in space-time between, I guess, the middle of space and the middle of time, which isn't really a thing in one-dimensional space and time. But like, you can't really. It's basically just putting a relative point and then working from it. The math's all the same. It's all relativity. It's all relative. Um, and that's the basis of math using these diagrams. Trying to think if there's anything else in this diagram that I won't address later. And I don't think so. But to recap, you should consider this our universe. It has a past time like infinity. It has a future time like infinity. It has positive and negative space infinities, which mean a moment in space time. Sorry, actually, I should mention that. I didn't actually go over that in the previous version I did this, but I figured it would be important for this. You can think of these bands, the horizontal ones, and then the ones that go like this, as moments in time across all of space. And you can think of these lines here, or these lines, as moments in space across all of time. And then the things between these are obviously moments, or like you don't have to follow these lines, but like a line through this would be this green line here would be an immortal being's path through space-time. So you can see they accelerate, they go around, blah blah blah. Maybe they have kids here, I don't know, raise a family, and they go to the end of time, which I don't know, would be fun. And light cones are directed towards the future because, well, there's some graphs that use them at 45, but these ones are at 90 degrees. And the next slide will go over an extension of the Penrose diagram, which shows the Penrose diagram when a black hole is introduced. So here we can see the same type of diagram. This is the Penrose diagram for the previous thing, and then this is a black hole, 2. 1 is our universe, 2 is the black hole, and you'll notice there's a singularity here, breaking the line. You'll notice this line here, which I said was like a boundary line. So this is the event horizon. These are all horizons. The question for these 3 is, what type of horizon are they? And think of them more as boundaries than horizons. But for when we're crossing into a black hole, that's an event horizon, and that can be crossed. These, because there's nothing to cross into, can't be crossed. You just don't reach the end of it. But for where there's something to go to, actually, maybe I shouldn't speak so hastily because perhaps there is a way. But whatever. We're only focusing on basically these 2 seconds right now. The singularity, you can see, I mentioned it previously, is that when you pass this, it becomes the future, where the space and time coordinates may switch. Now, I don't know if you can see really the color. Actually, you probably can't. It's kind of a bad diagram. It's kind of hard to find these diagrams. I'm sorry. But it's the same past time-like coordinate, same future time-like coordinate, same space coordinates, but you'll see we can actually cross the plane this time. So I talked about causality a bit, where you can't, I think I mentioned causality maybe, where you can't influence the past, but I should explain that if you were here, like in space-time, you can't influence something here because your light cone would have to be more than 45 degrees from its already 45-degree point, because you can't move faster than light, and light moves horizontally through space-time, as you can see through these photons. Light is the basis for our graphs. It's the basis of how fast an object can possibly go through space-time, and that's what we make all our boundaries on. And you'll see as we cross the event horizon, we go to the black hole, and we can't go out of the black hole because you'd have to go more than 45 degrees to get out of this section, which is explaining mathematically the gravity, or the problem of you can't get out of the black hole because the gravity is too strong. Like once you enter it, you're stuck there because you can't go faster than light. And for the next section, I will talk about the kruskal-szekeres diagram, which is where you remove these boundaries, and it shows a few other sections which I'll explain. this is I call this the somewhat extended Penrose diagram because the maximally extended one is the one we'll get to in a second. And that one is a lot more complicated, um, but it's really cool. And so what you should what you should remember from this slide is that there are now two sections. There's our universe, there's a black hole, um, and you'll see the black hole. Sorry, I should say the black hole starts from a point in time. It's not immortal. It doesn't start from the beginning of time. It pops up, and then we are able to go through it. It doesn't pop up here, or I guess I'll show you where there's a problem if it pops up. Um, and once you pass, the singularity becomes your future because you can't escape the you can't go more than 45 degrees to escape a black hole. And yeah, okay, next slide. So this is the KS diagram I talked about, and it is showing the same thing as the Penrose diagram. If you look at these two sections, this is our universe, this is the black hole. I'll talk about these two sections. I'll recap like basically the difference between kruskal-szekeres and or kruskal-szekeres and the Penrose, and then I'll talk about these two sections. But the difference between kruskal-szekeres and Penrose is that this one clearly doesn't have bounds on, like there's no square here to show, and it's because they don't want to put arbitrary limits on the size of space-time, which really shouldn't have limits on them. Or like mathematically they are able to, but if you think about going back to the boundary, like how I couldn't really explain why there's a boundary on the right side or on like the bottom left. I can explain the bottom left one after we look at other stuff, but on the right side it doesn't make sense to have a boundary because there's nothing for them to go past. Like there's no place to go to. And this graph is like the basis for that. So, oh, I should also talk about coordinate transfers. So these are all versions of the same first graph we saw at the beginning, where as the radius, well, I guess, hold on, maybe I can draw it, like a quick one. As the radius decreases, of the, like if this is the event horizon, as the radius decreases, the light cones become more and more tilted this way. Um, and this is all the translation of that. So coordinate transfer is the same thing as if you were to transfer, say, like I'm trying to think of a different coordinate transfer. Like if you're transferring y equals mx plus b to a logarithm. Like if you had, hold on, let me erase this. Wow, this is a terrible tool. What, I have to individually click everything? All right, sorry, I'm used to better tools, I guess. But if you had a y equals mx plus b graph like that, then if you made it a logarithmic graph, it would look more like that, I guess. Um, but it's the same translation. It's just based on the scale. So you're not actually changing any of the relative components. You're just changing um, how you measure it. And that helps us visualize different parts of the graphs for different situations. Uh, there are definitely some situations where you want to use this one, and that's for non-spinning black hole. For spinning black holes, it's much easier to use Penrose, and for also when you're talking about relation to other objects, it's way easier to talk about using Penrose because there are boundaries and you can easily see how objects interact because you just have to follow the 45 rule and that's it. But this one is a little more complicated. So coordinate transfer is just a way of transferring information or transferring a graph from one graph to another. I'm saying this because for some of you, it's probably very intuitive and easy, but I kind of struggled with it when I first was learning about it because I got a bunch of graphs thrown at me. It didn't really make sense how they all work together. But if you keep in mind that these are all the same, they're all representing the same thing, just at a different, like with different lines here, basically, then hopefully it'll be easier. Um, and the next diagram I'm going to talk about will be the Penrose diagram, more extended to show it's like the basic. Well, we went over the basic one, but it's like the not the maximally extended, but the extended Penrose diagram. But first, let's talk about these two, or maybe I'll just tease them. But you'll notice there's a singularity here, and also this starts at. Well, actually, should I? Because this one doesn't have a past time infinity, or it does, but it's like not directly shown. So actually, I'll show in the next diagram because I think it'll be easier to follow. These kruskal-szekeres diagrams are kind of hard to show stuff with. That's why people use Penrose diagrams basically all the time to talk about this stuff. And kruskal-szekeres are for very specific cases. So I'll get to that in a second. So this is the extended Penrose diagram, and it shows this is our universe. Well, you'll recognize this is our universe. This is the black hole. And cross over to this. I guess the event horizon is not really shown, but there is an event horizon, and then you'll see these two that are region, and you're like, okay, what is that? Um, so the idea is that a black hole started at some point in time, but that means that there had to have been something before that point in time. So mathematically, we can show this by having something called a white hole, where if a black hole sucks in all objects, a white hole pushes out all objects. And you're like, wow, that's crazy. I wonder how many there are in the universe. Well, as far as I'm aware, we haven't found one yet. I'm not going to make any definitive claims because maybe somebody's delusional enough to think that we did, or maybe I'm just wrong. But I'm like very, very confident that white holes haven't been proven to exist, but they mathematically should exist. So if you're like concerned about the fact that we know something mathematically that we can't prove, then I mean, I guess, well, one, welcome to theoretical physics. Two, I kind of have a non-official way of thinking about it, which is um, like the ejection of all matter from like a point. I think of that kind of like how you would picture a Big Bang, but I'm sure that's not actually the Big Bang because that would have caused everything to happen. Maybe it did. I don't know. Maybe I'm actually a genius and I'm right, and somehow the Big Bang is a white hole. But I doubt that I just came up with that on my own. But the important part to know is that things from these three universes cannot affect this universe. So we can see, like we can observe stuff that comes out of this universe because we can't go past 45, obviously. That's the beauty of Penrose diagrams. They make it really easy to see what can affect what can affect what. And we can an object can go from here to our universe and we can see it, but we can't observe any object here. So this is out of reach to us. But we are not out of reach of it. So a little scary, but I'm sure there's nobody or nothing in the white hole theoretically that would want to us harm. Um, and also, I should probably go over the scale of these diagrams. So if this is past time like infinity, this is future time like infinity, then our lives are probably like um, maybe the quarks inside of an atom for an LED in the computer, probably smaller. I mean, I guess theoretically it would be literally nothing because it's infinite. But if we think that time started at some point, which Big Bang maybe, that's our best theory. I mean, nobody actually knows the Big Bang's right. I'm sure there are some people who would argue with me that we do know that, but conclusively, the scientific community hasn't really like, oh yeah, this is 100% because I mean, it's kind of hard to do that thing. I think it's right. I don't know. But if the Big Bang started here, and this is like the future or the collapse of the universe, I guess, then we could measure our lives, and it would probably be about that scale. If I had to guess, I mean, this is imprecise, but like thinking about it reasonably, our lives are very, very short. Um, and you'll notice that the white hole feeds directly into the black hole. So the idea is that the white hole kind of ends, I guess. I don't know if that's the right word, but the black hole comes from the white hole. So, well, no black hole has been observed to come from white hole because we haven't observed the white hole, but we know where black holes come from, and that's from the collapse of stars. So, like when a star dies, it collapses. I mean, obviously, and then it becomes a black hole, or sometimes it doesn't become a black hole. Most of the time, it's become a black hole, but sometimes it does. There are black holes throughout the universe. We have one at the center of our galaxy, supermassive black hole, um, which has a spin, which I should go over because I said it's going to go over spinning versus non-spinning. This is probably where I go over. So spinning black holes are different from non-spinning black holes in that they change the singularity and they change the shape and they change the interaction with the environment and they change the graph, which we will see how the graph kind of is different between the two because you might see from looking at this think, oh, Penrose and kruskal-szekeres are kind of like the same thing. It's just one has boundaries, one doesn't. And that's correct. But we use Penrose to show spinning black holes because spinning black holes have a much more interesting, maximally extended graph form. Um, and spinning black holes, like the ones at the center of our universe, are the only known or the only found black holes in our universe, as far as I'm aware. I can't possibly think of a reason that there could be a non-spinning black hole that we would have found, because the odds of it happening are so unlikely given that when a star dies, which is how we know a black hole to be created, um, the star has a spin, and momentum can't be destroyed or created. Um, or maybe it can't just be, energy can't just be destroyed. So if something has momentum or a spin, which I'm going to be careful here because spin is used in quantum physics, and that's a much more interesting and kind of weird term, but the spin of a black hole um, continues. The spin of a black hole comes from the spin of the star as it collapses. So stars rapidly spin as they collapse, and then they become a black hole, and then bang, where's that energy? That doesn't just stop. So all the black holes we observe are spinning. And that means that we can observe in nature a lot of the properties that make spinning black holes seem more feasible, I guess, than a non-spinning black hole. But they also have some weird things. So the I would say a major component of like spinning versus non-spinning in terms of feasible or reasonableness, I don't know, reasonability, is that um, spinning black holes have, or sorry, non-spinning black holes have a singularity, which is like a point. And a singularity is something that, well, you'll notice, I mean, you don't even have to see a non-spinning diagram to see, but at the singularity, we can't see that until we're at the singularity. And in fact, because light cannot go backwards in time, you won't, if you go inside an event horizon, if the singularity becomes your future, but you won't see it until you're at the singularity. So you're basically traveling blind. I mean, if you survive, you're traveling blind um, inside a black hole until you hit the singularity, and then whatever. Non-spinning, it's kind of strange to think about because how could that happen? It's like there's a point just somewhere, like a singular point, which like a dimensionless point makes no sense as a point where we are forced to go because we have. I mean, we're three-dimensional, but we're in four-dimensional space-time, so how can there be a single point? Um, and it doesn't make sense, which is why we don't really. I try not to think about non-spinning black holes too much because they're kind of freaky and they don't really make any sense, and they're not found in nature, but they're important, like as a fundamental level. And oh man, I had a thought about something I was going to talk about, but I can't remember. Anyway, for spinning black holes, this is not the case. Where for spinning black holes, you have instead of it being like a point, um, you have a ring singularity because if you think about a point like if something's spinning, then it's a point revolved around an area, and that means that it's a point revolved. That's a ring, and called a ring singularity. Some people have coined it ringularity, and I like that a lot. That was Kip Thorne, I believe, or maybe I don't know. Kip Thorne's the lead science director for Interstellar. I'll probably be talking about some of this stuff later as we get more into specifically Interstellar. And he's also a very accomplished physicist. He didn't just like, oh, I'm the Interstellar guy. I mean, he is an Interstellar guy, but he's had a very very long history in his career. He's old as heck, and very smart, very good science educator. Um, I'm a big fan of his. Obviously, I mean, I'm making presentations about Interstellar, so yeah, what can you do? Um, but for ring singularities and for spinning black holes, um, it is possible to enter the event horizon and not hit the singularity. And that might be weird to think about because it becomes your future. Or in a non-spinning one, it becomes your future. But in a spinning one, the geometry kind of changes a bit. And I'll show you in the next slide about the maximally extended non spinning black hole, which kind of has some weird, quirky stuff. I mean, obviously you'll see, but it's exciting. So hopefully you'll have fun. So I realize now I never actually talked about the other section, but if we look at this is the maximally extended, it's a little cut off. I don't know if that's my fault or if that's just how the diagram is and they're trying to be cheeky, but this is our universe. This is the universe we started with, the first Penrose diagram. This is the black hole. This is the white hole. They mark it up here. and then here is a parallel universe, which I don't actually think I talked about. I think that was a mistake. Um, but yeah, the idea that there's a parallel universe we can't access, but that can affect a black hole and can affect then our universe and the parallel universe can both affect a black hole. So this is called an einstein-rosen bridge. That's something I'll get into a lot later when we talk about wormholes. This is already talking about wormholes, and it shows a wormhole, but I'm not going to get too much into it because this is just about graphs. Well, I guess it's become a little bit more than just graphs, but the basis of this is just about graphs, and the whole Einstein-Rosen bridge thing is a whole new thing, whole new can of worms, a whole section, I think a whole chapter, maybe just like a whole half of the lecture series. I'm not sure, but maybe it'll just be a chapter. But anyway, notice that we can go, if we're in our universe, we can go through a black hole. We can kind of skirt around the singularity and enter through another event horizon into another event horizon, and we'll go into a new universe or a new parallel universe. This is basically showing that with spinning black holes, it opens up the possibility mathematically for travel through universes, through our universe and other universes. If this is feasible, I'll get into that. If this is physically possible, I'll get into that. If this is even like mathematically possible, I don't think I can get into that because it's like crazy math, but the diagram, the graph math works out. So, you know, um, there's some people who vehemently disagree with this model because they think it's ridiculous to think about parallel universes, but I think that's no fun, and I also think you can't really say it's not. It's kind of like maybe that's appeal to ignorance. Never mind. But it's like you can't really disprove something because it's theoretical. And if you could disprove something because it's theoretical, then all of science would exist. So, whatever. Um, and oh man, what was I going to talk about? Oh yeah, so the geometry of spinning versus non-spinning black holes. That's going to be my next lecture, I believe. Um, and then I'll also talk about like light in relation to how a black hole affects light for like outside observers, which is an important thing for Interstellar because they show picture they show not pictures, but they show black holes, and I can get into like the caustics and the visual effects of a black hole. Um, but for our purposes, you should know the reason that you can travel through a non-spinning black hole, or sorry, through a spinning black hole, which you can't actually probably unless you're like crazy, like superhuman, and can survive unbelievable forces. Um, then you probably couldn't do that. But um, the reason is because the spinning black hole has a much different geometry where it actually has two event horizons. So you'll notice the black hole has two event horizons. I kind of glanced over that, I guess, but we have the event horizon we can enter, and then we have an event horizon over here. And that's kind of the same as the geometry of it, I guess, where it has an outer event horizon and it has an inner event horizon. Um, and once you're inside the outer event horizon, the inner event horizon becomes your future. But once you're inside the inner event horizon, you can move around the singularity and go to another universe, which is what this is showing, basically. Um, and there's also something called the ergosphere, which is where, because it's spinning, space-time is spinning, space-time around the black hole is spinning around it. It's not just like a spinning object and then, oh, eventually you hit the event horizon and you go through and then you're spinning. No, it's because it warps, just like any other spinning object, it warps space-time around it as it spins. And that means that there's a part of the black hole where light can escape at some angles, um, but not all light can, and where humans can't escape. I mean, obviously there are points in like even in non-spinning, where light can escape and humans can't. But for a spinning black hole, it gets a little weird. The ergosphere is a little weird. I'll get into that obviously. Um, and I figured, okay, I guess the takeaways from this slide are there's the idea of multi-universal travel from using spinning black holes. And spinning black holes have um, like they have different geometries than non-spinning black holes. And also, you should notice this goes on forever. So theoretically, the um, black hole, wormhole, universe, whatever, white hole could goes on forever, and it does go on forever. And this is just for one black hole, so take that with a grain of salt. I would question how accurate this is to real life because we're not taking into effect conditions like charge, which don't have a very large impact on black hole geometry or much of the physics or energy of it. But we talk about that a little bit when we talk about the black hole information paradox, and that's something that talks about like the real life applications of black holes, which would get into how feasible is this graph. The black hole information paradox is something for the wormholes unit. I believe I might put it in the black holes unit, I guess, because it's only about black holes, but it's relevant to wormholes, so I figured I should put it in the wormholes section. And then I'd also talk about the Casimir effect, which is another possible reason this couldn't exist. Um, and that will definitely be in the wormhole section, but basically it's like the idea that a wormhole would close up before anything could get through it. Anything with mass could get through it because of how space-time around wormholes works. So the travel, if it was possible to actually travel to these places, right now, no, but mathematically, it's theoretically possible. And I hope that this was satisfactory for correcting some of the things I said. Um, Maybe I should mention the thing I drew in real life. It was like this box, but then I had like lines going like that, and that's just not accurate. It should be only lines um, that are horizontal and vertical to show that. And then I also showed that um, this was all, I didn't show like the split between uh, these four. I just showed that this was all, like I started in this section, which is the white hole section, and that I don't know what I was thinking. I think I was just rushed and I was trying to get stuff done, but I apologize. Hopefully that will happen again, but I expect I will have to make more corrections in the future, and I'm happy to do so because it's basically just me being able to talk for as long as I want about the same thing, and I think it's also easy to understand. Um, Hopefully, I will not be lazy and I will attach a problem sheet to this video because I was requested that if I provided some kind of worksheet, it would help people like remember stuff, and I agree. I know that having worksheets is like scientifically proven to um, making your brain do work to do stuff is makes it much easier to remember stuff. And I do that because I like asked ChatGPT to like quiz me on stuff for this presentation because I don't read the things, I just remember them. Like you have to actually put work into it. Um, so I'll probably get ChatGPT to write some questionnaire, and then I'll like put the answer key, and I'll have that in two separate forms. Hopefully I'll have that linked at the below this video. I also should say that I don't use ChatGPT to make any kind of script. I just use it to learn about things that I can't understand through other sources, or if I'm trying to quiz myself, or if I'm trying to make quizzes for other people. So, and I also don't support generative AI for images, so I will not be using that for any of this, even though I'm sure it'd be helpful in some way. But there's just so many other sources out there that I wouldn't use AI on moral grounds, and also accuracy grounds. It wouldn't be very accurate either. Um, I hope you've enjoyed this presentation. I've already given it already, so I'm a little annoyed, but hopefully I didn't make it too miserable on you guys. And next presentation will be it'll be when I come back from break, or maybe I'll do it away, just like I did this presentation. But I guess I'll see if you guys can like tell me how well this worked as an education thing. Then maybe I could do it like that. And also, it is after 12 o'clock at night, and I want to go to bed because I didn't really get much sleep. So, good night. Thank you for watching, and I'll see you in the next lecture.